Recording in progress.
Okay. And do you need notes or you're good?
I have notes. Yeah.
Okay, cool.
I got all
All right. Okay, cool. Great. All right. So remember we talked about symmetry, right? The first page of part 2. Yeah. So that's going to be page 9.
You can?
Actually, page 9.
Yeah, I got to do a correction here. So I'm not totally off, but there's something I need to add. So let's take a look at 3 cos theta again, but let's actually kind of just think about this more slowly. And again, polar is kind of tough. It's like learning a new language because you guys have done rectangular for so many years. Polar is kind of this new thing, right? And there are advantages to polar, obviously, like with rotation and all the other things we want to do. But here's the deal. If your graph is symmetric about theta equals 0, or theta equals 0 is kind of like the x-axis, we call it the polar axis. So if graph is symmetric about it, for example, if I were to plug in, say, I don't know, actually, have some Zoom. So let me do on Zoom here. Say, for example, I had theta is pi over 3. If you plug in pi over 3 into that equation here, what do you get for r? What's cosine of pi over 3? So you get 3/2. So you'd probably get like a dot over here somewhere, right? Now let's switch the sign of theta. If you switch the sign of theta, what's r going to be still? Still 3/2, right? I mean, the cosine of negative pi over 3 is 1/2, but then times 3, you get 3/2, which would be over here, right? Because remember, when you plot this point, you plot that angle, what direction are you going in? Counterclockwise or clockwise? What's next? Clockwise. So you're going clockwise at what radius? 3/2, right? So you got to be in between circles 1 and 2. So cool. Okay. So that's what we get, right? Now notice, are these symmetric about that horizontal axis? They are. Theta equals 0. They're symmetric about it, right? Because if I were to cut this out and fold along this line, these 2 dots would map onto each other. So we expect that to happen, right? Also the fact that if you replace, it says here, if you actually it says it down below, but if you replace r comma theta with r comma negative theta, you get the same angle. So if r is replaced with r itself, but theta is replaced with negative theta, and you were to evaluate cosine negative theta, you get the same equation as you had originally. So that would guarantee that kind of symmetry. Here's another kind of thing that can happen as well, which I didn't talk about. You need to add this to your notes. Negative r comma pi minus theta. So let's think about that one. Pi minus theta is kind of a funny one. Now, if I have pi over 3, right, as my theta, now tell me, what's pi minus pi over 3? Sorry, say it again? 2 pi over 3, thank you. 2 pi over 3. Ah. Okay, 2 pi over 3. Now, if I do cosine of 2 pi over 3, what's my r value going to be? Negative 3/2. Now let's think about it. How that point look? 2 pi over 3, and I rotate counterclockwise, how many degrees? Or like, yeah, 120 degrees, right? So it'd be somewhere over here, right? But what's your r value? So it's got to split 180, right? And so it's back to the same place as what it had previously with 3/2 comma negative pi over 3. So it comes back to the same place as it was with the other point we had. So this is equivalent to 3/2 comma negative pi over 3. It's equivalent. So that's another type of symmetry we have to look out for as well. If you replace r comma theta with negative r and pi minus theta, that'll work. The same thing is going to happen with symmetry with about pi over 2. Pi over 2 is a vertical axis, clearly, right? So the same thing's going to happen. Like if I replace theta with negative theta, of course I get negative r. You know, I did talk about that. But if you replace theta with pi minus theta, so for example, what if I have like pi over 6 here, right? What's not pi over 6? So that times 4 2, right? Now, what if I decide to do pi minus theta? What's pi minus pi over 6? 5 pi 6. You did 2 pi. 5 pi 6. What's sine of 5 pi 6? Is it still positive? Yes, in Q2, which is still 1/2. 4 times half of 2. So now you're over here. You got to rotate 150 degrees with 5 pi 6 at a rate of 2. Are these symmetric about that vertical axis? Yes, they are. If I cut out a square piece and pull along that y-axis, or like this one take is 5 and 2, these two dots map onto each other. So that's yet another type of symmetry that I didn't talk about. No, sorry, another way of proving that symmetry. R comma pi minus theta.
Could you say that -3/2 2 pi over 3 is equivalent to?
Oh, to 3/2 common negative pi over 3, which I did originally by switching this the sine of theta. So when you switch the sine of theta, if you get the same r value, that's going to be symmetric about theta equals 0.
2 pi over 3 is not the same as -5.
No, but negative 3/2 comma 2 pi over 3 and 3/2 comma negative pi over 3 are the same.
Oh, yeah.
Okay.
Okay.
I know it's very mind bending. I know, I get it.
It looks like the directions are 100.
Correct, correct. So you may want to update your notes in this part as well. In order to prove this kind of circuit for pi over 2, replace r and theta with negative r and negative theta, you should get the same equation. Or you can replace theta with pi minus theta and r with r, you should still get the same equation. If you actually wanted to prove that symmetry using pi minus theta, you can use the difference formulas and actually would prove for you. Likewise over here, if you replace theta with negative theta and just keep the same r, or if you replace theta with pi minus theta and r with negative r, you'll still get the same equation, guaranteeing the symmetry about theta equals 0. Theta equals 0 is the horizontal axis. So that's something I forgot to mention that is important that you guys know. That there's other ways of proving the symmetry, not just switching the sine of theta, but switching theta with pi minus theta, and then changing r, keeping r, depending on what symmetry we're looking at. Okay. Hope it all makes sense. And everything else was fine. I don't think I made any other mistakes elsewhere. So I think everything else is okay. I think we're all good. Remember we had all this stuff, right? That was all fine. Remember we had all this stuff as well. Did we go? How far did we get with this? Did we get through all this?
We didn't get the correlation.
No, I know that, but do we actually let's talk let me redo let me recap part C just to make sure we're clear on everything, because this is all brand new stuff. So let me recap this part. And then so even though you have it filled out, and then we'll move on to cardio curves, okay? And our plan for today is to finish off part 2 of these notes, to kind of get to very, very ambitious. Page 18, we'll see if we can do it. I got faith in us. So here we go. So buckle up. All right. Okay. I'm just going to recap this part just to make sure we're all clear on what's happening here. So let me get my pulled out notes. So I'm making more mistakes. Okay. Here we go. So let's take a look at 2 plus 4 sine theta. Okay. So if we look at a range from 0 to 2 pi, so it takes range 0 to 2 pi, draw one complete graph, change range to 0 pi, view the graph. What do you notice? So let's go back to that graph one more time. So Desmos is our friend, right? Desmos is our best friend when we're doing stuff. And thank you, Kieran, for teaching me how to change this. I appreciate it. I feel like so much better now at this stuff. You only told me about that, right? Switching. Who was that? Oh, Tor. Thank you, Tor. Oh, okay. Yeah. Sorry, I should give credit where it's due. My apologies. Okay. So R equals 2 plus 4 sine theta. Okay. So we have this, right? Oh, sorry. I should get, yeah, my bad. Sorry, Lauren. So we got this, right? And remember, we said about the inner loop. It's kind of hard to tell, but that's a raised to 2. because you have 4 minus 2 is 2, and that's 6, because 2 plus 4 is 6. You're looking at absolute values of these, like we call it A and B. So you take the difference of those, you get 2. Remember, it's time. The orientation is, what was that?
No, sorry, I'm just a little lost right now.
Oh, okay. That's a lot you missed.
I missed some stuff, so.
Didn't watch the.
Yeah, you missed a lot, dude. All right. Anyway, now let's say I switch this to theta pi. Okay. So it doesn't do the inner loop part, right? So if I don't do that, then we have nothing below. So what do you notice? There's no curve below theta equals 0. The algebraic determine the zeros. I mean, if I just replace r with 0, right, and work it all out, it's not that hard. Sine theta should equal -½ I think. So what's theta equal? 7 pi over 6. And 11 pi over 6. We got that, right?
No curve below.
Exactly that.
There's just no.
No inner loop. When I restrict, yes, thank you, Sebastian. When I restrict the domain, I don't see the entire curve. See, when I had 2 pi,
Curve meaning no inner loop.
yeah, the curve doesn't exist below. Okay, what's actually happening? Think about it, right? If you go from 0 to pi, like if I plug in 0, I should get 2, right? So I get 2 right here. If I plug in, say, pi over 2, I should get 6, which is up here. If I plug in pi, I should get back to 2 again, and then I stop. I never see this other part. I never see this part where I loop around like
So
this.
that's no curve below theta equals 0 or
Exactly.
above theta equals pi.
Theta equals pi.
We restricted.
No, there's a curve above theta equals. Well, no, theta equals pi is like based on the horizontal axis. The bottom line is we don't see the inner loop.
Is that because? That's because.
That's because the inner loop is created from pi to 2 pi. Pi to 2 pi creates an inner loop, right?
That's not. So that's.
So right, so
there's
this
no curve between pi and 2 pi, not below theta equals 0.
no, theta equals 0 is this, the horizontal axis. I don't see any part below.
Saying it as a
Yeah.
line.
Yeah,
Okay.
yeah, you're overthinking. Careful about that. Okay, let's keep moving, guys. Correct. Okay, guys, let's keep moving. All right. So now we got that done for. And by the way, at 7 pi over 6, 11 pi over 6. Okay, so remember, guys, quiet, please. Remember, when you have the zeros of the function of the polar curve, when you have zeros, it's be touching the pole, right? So 7 pi over 6, like if I continue plotting this, like right now this is at pi, right? If I do like, I don't know, something slightly bigger than pi, like 3.2 or 3.3, you can start doing this, and all of a sudden it hits this right here. Right where I'm pointing, that's a 7 pi over 6. Then it loops. Then it kind of loop like this. As it keeps looping, as it gets back to the pole, what is it getting closer and closer to? 11 pi over 6, because it touches the pole again. Then it finishes off from 11 pi over 6 to 2 pi. So essentially what's happening here is that this portion is occurring between pi and 7 pi over 6. Then this portion is occurring from 7 pi over 6 to what? 11 pi over 6. And then this portion is occurring from 11 pi over 6 to 2 pi. So I want to make sure we're just clear on the order of which things are happening. So the red is from 0 to pi, then this little portion is from pi to 7 pi over 6. This loop is from 7 pi over 6 to 11 pi over 6. And using a sense of symmetry.
Oh, that's why we find the zeros, because that's where it intersects at the.
Correct.
four.
Right. So this part right here, let's just kind of focus on this. The right half of the inner loop. What do you think the theta values are correspond to for this right half of the inner loop? From 7 pi over 6 to what?
9.
9 pi over 6 or 3 pi over 2. Because if you think about it, if you do 3 pi over 2, what's sine 3 pi over 2? -1. And what's 2 plus 4 times -1? So you have -2, 3 pi over 2. Which should be 3 pi over 2 is over here, but we have a negative r, it flips us back there. So that's why that's happening. And then we keep going until we finish off the loops.
Wait, we have a negative on? Focus on.
Right. Okay.
How do we have a negative?
Oh, okay, when I plug in 3 pi over 2,
Uh-huh.
what's sine 3 pi over 2? I'm just plugging back into the
Negative
original
1.
equation. -1, right? What's 2 plus -4? Exactly. That's why I have a negative R value. But we have a negative R value
R is a negative.
and you
Oh,
rotate
it's-
180.
It's opposite, okay.
Exactly. Yeah, very mind bending stuff. Totally. Okay. So hopefully we're okay with that. Okay. Now, what range of values produces that? Well, I know now that's going to be from pi to 2 pi, right? That produces the inner loop. I know this now. But more specifically, actually, let me take it back. Truly, it's actually this. Truly, it's that. Because, so you might want to make a correction to your notes. Because what's happening again, when we look at the curve one more time, that was just from 0 to pi, right? And again, this part right here, that was from 7 pi over 6 to, sorry. That was from pi to 7 pi over 6. So it wasn't truly the inner loop. Truly the inner loop was that right there. And then this part, let's switch colors one more time. We'll say we do purple. And it blends with blue a little bit. Sorry about that. That's 11 pi over 6 to 2 pi. So truly the inner loop was actually 7 pi over 6 to 11 pi over 6. Okay. Yeah. Yes. No, some might make like a unit test.
Yes, this is your turn. You might have. No, they were both.
In Geo honors, I don't know.
Yeah, the 9 kilos.
Okay, let's talk about this again, about symmetry. So I want to make sure I'm doing this right. Okay. So anyway, find the points where it crosses that stuff. Well, that's easy. So if you think about it, R equals 2 plus 4 sine 0. So R equals 2, so 2 comma 0. Also, if I plug in what was going on? Also, you have to do this as well. Yeah, so I kind of I think I was rushing this on Tuesday with you guys.
Yeah, 4 sine pi.
No, guys, I'm focused on this right now.
Oh.
Yeah, let me color code this. Okay. Let's. We have to be super complete here. Think about it. When theta equals 0, that's horizontal, right? What's also equivalent to that? Theta equals pi. That's 180 degree rotation. So I have to plug in pi as well when investigating this. So 2 comma 0, 2 comma pi are actually points that cross theta equals 0. Right? Because 2 comma pi is still the same thing. Because the line theta equals 0. Just to show you the polar plane one more time. Again, I'm going to draw a polar. Yikes. Okay, sorry, it's a little messy there, but remember, we have a dot right here. And a dot right here. Right, remember we had those 2 dots there. So that's where they intersect. Now for pi over 2, Let's go to red. That's 2 plus 4, which is 6. So 6 comma pi over 2. And then, but remember, what's also on the same line as pi over 2? What other angle is also on the same line? You gotta investigate that also, which I forgot to do with you guys. Or didn't realize I had to do. So
Is that R one?
R. So 2 minus 4, it's -2. So 3 pi over 2 is like negative y-axis, but because it's -2, it's got to flip. So here's the proper order of how to graph it. The proper order looks like this. It starts here, hits this, goes below a little bit, hits a pole, loop, loop, go down, and does that. That's the order in which it does it.
Like the lowest point.
Oh, this right here? That's calculus. You will do that next year in Ms. York's class, in AP Calculus BC. That's like an extrema. We won't cover that in this class. Okay, verifying symmetry. Let's look at that really fast. Okay. So just by looking at the graph, I mean, it's pretty darn obvious. Going back to here. Let's go back to 2 pi. I mean, it's pretty obvious. And this is where I messed up. I didn't quite do this correctly with you guys. So I want to correct myself here. What line is going through the middle of this graph? Theta equals what? Pi over 2. Not theta equals 0, clearly. Not anything else, just theta equals pi over 2. So we have that symmetry, okay? That symmetry is there. Now here's the thing. Going back to notes again. Here are the filled out notes. In order to guarantee this kind of symmetry, we have to do one of two things. Replace r comma theta with this or with this. Now, if I tried doing it this, but it didn't work out. So I'm going to do this instead. Let's see what happens. Okay, so here's the deal. And this is the part that really kind of makes polar not fun sometimes, but we have to do it. So to verify,
You can only do one out of the 2 methods.
yes, correct. You gotta be persistent, try both. So great question. Yeah, that's what you have to do. So here's the thing. Clearly, the graph of R shows that we're on page 55 now.
Over the decimals for 3 seconds and
It's all good. It's all good. We're on the same page, dude.
David, look. Remember this problem? Look, it's slightly low.
Yeah, he hasn't even been here this week. He's telling me what's up.
The fact
We're just giving you a hard time, dude. It's all good. Okay. So clearly the graph R shows that symmetric about theta equals pi over 2, right? So either. Sorry, let me reword this. So replace R comma theta with either negative R, negative theta, or R comma pi minus theta. Until you find it, until it works. It'll work for one of them.
It doesn't work for you.
And you know you did
Then you get just give up. Just give up. All right. So let's do so guys, let's do this one here. I'll do in pink. Let's do that one, right? Okay. So replace R with negative R. 2 plus 4. Now what happens when I do that? Okay, we have a problem. we have a problem when I do that. Because we're trying to prove this, the symmetry of pi over 2, because the graph shows that, right? Because that's what we have to prove now. Problems that replace arc, and we saw earlier on, like, oh yeah, if I replace, it's like an arc function, replace theta with negative theta, I get negative r, right? When it's have this kind of symmetry. But the problem is that doesn't happen, right? Replace theta with negative theta, I get negative sine theta. So I get 2 minus 4 sine theta, and that's negative r. That's a different equation. So this failed for us. Right? It didn't work for us. So this is no good. So to answer your question, Zaid, how do we know? You just got to try both until it works. If this worked, then you're done. Don't try the other one. You're done. Exactly. Yes. Correct. Yes.
Are we gonna have to remember those?
100%. Yes. I know.
Never was.
Odd even function for sine, cosine, sine or odd functions, cosine or even functions. All right. So let's replace r with r. And 2 plus 4 sine. Now replace theta with what again? Yeah. Now this is where the fun begins. Oh boy. Okay, you're gonna have to use. Yeah. Yeah. And I realized this at the end of class on Tuesday, like, oh crap, we only have a few minutes left. Okay, I knew how to self-correct, which I'm doing now. I'm correcting with you guys right now. But it's good we're talking about this again, because this is new stuff. It's hard stuff, right? We got to talk about this again. But it's good. You guys know some part. It's good. I will give it to you. Remember, I gave it to you guys anyway, right? I don't expect you to memorize. I'll give it to you. So let's just do it. It's okay. This is gonna be fun. Let's do it. Okay. So what's the sum formula? Oh, sorry. My bad. 4 times bracket. Okay. Yeah, it goes to Telskrian. Sine pi. Cosine theta. Love it. See, you remember. There you go. What are you guys moaning and groaning about? You guys got this. Cosine pi.
It's ingrained in my head.
Guys, not that hard. You guys got this. Okay, 2 plus 4 times. Now, what's sine pi? Goes away. What's cosine pi? So negative 1 times sine theta. Okay, see, it's not too bad. What's negative times a negative? Boom, got it. Now it's verified. Now it's good. We're verified.
Wait. And just the calculations are even.
Sine pi is 0.
Okay, just because.
I know we did a lot. Yes, go ahead.
Just because we do all that and then we come out with the same equation, that's how we know that it's
Yes.
about theta equals pi.
Yes. Yes. Okay.
Or times.
Yeah.
Okay, guys, let's back up a little bit. You guys quiet. Okay, I'll get your question in a moment. Okay. A lot of fun stuff, right? Okay. You guys are cool with the formula? Plug and chug? You good with that?
Yeah.
Cool. What's sine pi? 0. So this went away.
I forgot.
That went away. So John, that went away, right?
I forgot about.
Now what's cosine pi? -1. What's negative 1? Positive 1. 1 times that is a sine theta still. 2 plus 4 sine theta. You set. Got it. Okay. Now, Zach, your question. So let me also correct about that too. We can't really use odd or even symmetry with polar, because odd and even symmetry is actually very specific to rectangular coordinate planes. The problem with this, if I go back to Desmos again, right? I can't really say it's an odd function, because here's the deal. If I rotate, let me clear my screen for a moment. If I rotate this 180, what's going to happen? It's going to be pointing down. It's not going to be the same orientation, right? So I can't really use that kind of logic for this. The only reason why I brought that up is because it's similar, right? In some ways, like of course, sine negative theta is negative sine theta. That's an odd function, right? But to have symmetry about theta equals pi over 2, it's not going to be a rotation of 180 degrees. Not at all. It's simply symmetrical about a line, theta equals pi over 2. So we can't really say it's odd or even, because that really truly applies for rectangle. It's not polar. So thank you for clearing that. That's I'm glad you brought that up. Now I feel more complete. Now I feel better. Let's move forward. All right. Yeah, I know you spent a lot of time with that. Okay, so again, I had an ultra ambitious plan. So let's just do cardio. So we won't do dimple limicon, convex limicon. We won't do that. We won't do lemniscates. If you guys want to see how these look, just
I'm so excited to do content. Let me
Live this.
I know I was too. Okay. Before we do these, guys, quiet please. Before we do these, we've got 15 minutes. Before we do these, why things are called cardioids? It's like a heart, yeah. Heart, right? Yeah, there we go. They're gonna look like hearts.
Wait, so why is it called a card?
Like cardiology, heart. Yeah, like cardiology, cardiac arrest, or cardiac situations. The Latin roots, yes, yeah, or Spanish, or whatever, or French. Boom, got it. Yes. Now, we're not gonna do these today, guys. Quiet, please. Thank you. We're not gonna do this today. Yeah. Okay. I know you guys are having fun with this, but let me talk. Dimple limicon and convex limicon look like this. So we've done limicons already. So what we just did was a limicon, right? That had a loop. But sometimes these loops vanish depending on what's going on with A and B. So when the A value or the number that's not next to the trig function is larger, sometimes they go away, or sometimes become convex, become flat. We're not gonna do that today. And lemniscates are like barbells or dumbbells, kind of like that. Yeah. And then ultimately we'll get into like rose curves, which is really fun. Yeah, so we're not there yet. Yeah, so let's just finish cardioids. We can do the rest of this on Monday. And the more I think about it, I think the more I'm starting to realize I might have to push the small test out till after Thanksgiving. I might have to do that.
Maybe after the.
How about during Christmas break? You come in during Christmas break.
Maybe after the final. Maybe just don't do this on the final.
Maybe it is.
How's that sound?
Yeah.
This actually sounds hard.
Why just give everyone all A's? Just call it a day.
Yeah.
There we go. Okay. Easy for me. Yeah, I know. All right. Okay. All right. Okay, guys, let's do cardioids and we'll be done. Okay. All right, here we go. Cardioids. All right, so let's go from 0 to 2 pi. Here are my polar functions. R equals 1 plus cos theta, or these other three you see there. So as you're probably noticing, what's happening is that the absolute value of A and B are going to be the same. A being the number that's on its own, B being the coefficient of the function. If the absolute values are the same, we're probably going to have these cardioids. We have different orientations as well. So my guess is this is probably going to be horizontal. That's probably going to be right. That's probably going to be left. That's probably going to be up. And that's probably going to be down. And remember, generally speaking, what we were talking about, like the absolute of A plus or minus the absolute of B sine or cosine theta. So as long as this is true, you're going to get a cardioid. As long as those two, you can have a cardioid. Okay. The absolute of A equals absolute of B, where A and B are the numbers that are part of the function here. Where A is a number on its own and B is a number that's next to the trig function. Correct. So let's just do this in Desmos, see what happens.
It's R, so the equation is R equals A plus B cosine or sine.
Correct. Well, that's just generally for all the polar. Yeah, right. So you see what happens here? Ooh, this looks cool. All right, so here's your heart. I know. Okay. So think about it. A plus B adds up to 2, right? A, you're both 1 and 1. Adds up to 2. You kind of have this denser, I guess. There's no loop. There's no loop. How would I make a loop? Well, what if we put a 2 here? See, I get a loop. Or a 3 here. But then you get like something that's convex. We're not there yet, but yeah, or like 3, right? See all these different options you have. Or if you put a minus, it does this, right? So the graph will look like this.
Because, you know,
The ma-
what's
the-
red mean? Like, that's the one that goes
the
outside
major,
of
the major, yes, the major part, yes, right.
Goes to two.
Two,
Oh, because in the middle, the loop would go to one.
right. And what's happening here,
What stops the loop from being?
that's because A and B are the same value, that's why those are the same value.
So like mathematics are equal. Why does that do that?
Oh.
Yes.
And plus, if you plug in these numbers, right, you should get these values coming out for R, right? That makes sense. 5 over 2, 3, 5 over 2, you get 1. That's where it touches the 5 over 2 axis. Okay. Wish I got enough juice in my laptop.
What like
Yeah, should be fine.
makes it the cardio of A and B?
It's just as you go through the motions and plot points, you just get that. That's all. I mean, yes, well, out numerically, actually what's happening, David, is that these are the same. Yep.
What are the same?
This number, A and B.
I just don't know the.
It's just the nature of it. Just if you plot the points, this will happen. I mean, I think you're asking maybe a question that's probably too deep that Bay doesn't have an answer to it. Okay. All right, next up. What do you think is gonna happen here, guys? It's probably gonna hit 4. Okay, I'm doing a terrible job drawing these.
So negative, they go opposite.
Yeah, I'm doing a terrible job drawing these, but anyway. So we'll say this is 4 comma pi. This right here will be a 2 comma pi over 2. And this right here will be 2 comma 3 pi over 2. There we go. Yeah, cosine of pi over 2 is 0. So yes, sir.
Something that like R two R equals 2 plus 2 cosine theta is the same as R equals -2.
Right, correct. Yes.
So R being positive or negative doesn't matter.
Right, correct. This is by the way is 0 comma pi.
R equals
No, sorry, 0 comma 0. My bad. And that right there, guys, quiet, please. Thank you. And that's 0 comma pi, I think. Yeah. Okay. So that's kind of the rotation that's happening. Let's move on to the next page.
why is going 0 comma pi?
Just plug into the equation.
All zeros just the same 0 comma something. So the same.
No, but it depends what angle causes that to happen. It all depends on the equation you're doing. Like, okay,
Oh, because this one because it's on the right.
so why don't you tell me where am I touching the pole for this one? You tell me. You got this. What makes that -1? Okay, good. So you can have a pole at 3 pi over 2.
Oh, I see. Yeah. Okay.
Okay. So it's gonna look like this. Okay, a little bit better there. That's at 6 comma pi over 2. That's at 3 comma 0. 3 comma pi. And that's at 0 comma 3 pi over 2. Good. Hold on, Zaid. When you plug in 3, we'll sign 3 pi over 2 -1. 4 minus -4 times -1 is gonna be +8. And that's 0 comma pi over 2. Okay, Zay, what's your question? Okay. So, how do you determine whether it's going up, down, left, right, whatever, right? So again, we already talked about it, but if most of the curve is up or down, that will be sine theta. Or if most of the curve is left / right, that'll be cos theta. And of course, you have positive, negative, positive, negative. Okay, so that's a generalization there. Let's analyze one of these, and then we'll be done for today. Questions so far? I'll just wait a sec. Yes, go ahead.
Of like, can that be negative 2 sides of?
Wait, for the third one?
Yeah, 3 pi. Yeah, if you plug in pi, sine pi is 0. Yeah. 3 plus 0 is 3, it's just 3. It's okay. You're thinking of rectangular coordinates. It's on radius, it's on the circle, the radius of 3. At pi radius. It's not, yes, you want to say -3 because it looks like a negative x intercept. Don't think of that way. Yeah. Again, you gotta think differently here. Yeah.
Does A always have to be positive? Because if it's not.
True, in this case, yes, you are correct, yes. Well, we're gonna clear up, once we get all this done, we'll have our overall generalization. Just wait for that moment. Okay, guys, let's fast forward in the interest of time. Let me talk about the symmetry here really quickly. Okay, because we already know, guys, quiet. We already know how the curve is generated, right? We kind of already see it. Like, remember we had like, all these little parts here. Like, remember we had this little part like this. Like how when does that happen? When does this happen? All those things, right? It all happens like, when you're at different theta values, but let's focus more on the symmetry. So if we focus on correct. So 2 minus 2 cos theta. So 2 minus 2 cos theta was this one, right? And it was symmetric about what? Okay, so I need to use that symmetry. Okay, let's verify it. So this is symmetric about so all I'm going to do is replace r comma theta with either what? With either r comma negative theta or, correct, or negative r comma pi minus theta. Well, I think just by looking at kind of investigating what's happening here, let's just use this one because I'm pretty sure that's going to be fine, right? Because r is going to equal what? 2 minus 2 cos negative theta. What's cos negative theta? Great. What do you get? Same thing. Verified. That was easy.
So if it's cos, it's always gonna be.
It's an even function.
Oh, yeah.
Duh. Yeah, come on, David.
So cosine just always means it's gonna be.
Right,
symmetric
correct,
about
right,
theta.
right. Yeah, we'll bypass the rest of this for now because the other parts, because I think we understand how this is being generated. I'll recap it on Monday. Homework. You guys have the homework packet, the thick one. So now you can actually use that thick homework packet I gave you guys. Sure, go ahead, yes.
If you're trying to verify a symmetry algebraically, if it's cosine, you're always just gonna replace.
Theta with negative theta. Yeah, because it's easy.
Because it's always.
And make RR. Yeah. Yeah, exactly. Okay, so the homework packet. Definitely I think you guys can do. You definitely could do number 1. I think you guys can handle that. And I'll put the answer key up. Well, several parts there. I'll take care of it in a moment. We can't do number 2. That's gonna be rose petals, I think, which I really wish we could have done that today, but that's all right. So we can't do number 2. So really, your homework's pretty simple. Just number 1, parts A through G. That's it. It's just the first 2 pages. That's it. That's all your only homework is that. I know it's like a weekend for those for the play or doing other stuff.
But,
I get you last. So I'm gonna 20
a lot of stuff happens with them, you have a paragraph.
I want.
So,
So,
I don't-
I lost like over 3K by my buddy.
Back in, half the right.
Whoa, there was
Okay,
a couple of my dogs. You were like running away. You said it. It's so.
Oh,
funny.
$0.
No, look at this. Look at this.
Such an ugly dog.
But I gave you guys that.
Look at that thing.
You burn a seed.
Look at that thing. You're gonna wash
No,
it.
it's
It's
just
still
pretty tight. I'll get
brown.
them real fast. Hold on.
Wow, that's something that
Oh,
your
I
grandpa
lied.
would say about a person.
Not wrong. There's like a wild nursery rhyme that I like. My mom showed me.
You want to?
No, it was like hella racist, hella poetry. Yeah, it was like.
I don't see your homework packet. No, all right.
It was like about. It was
It's this Friday, so.
Yeah, it's like it was one.
Don't see you guys till Monday.